Ladies and gentlemen, this film is brought to you by Capandball and the Mohács 500 research group of the János Pannonius Museum of Pécs, Hungary. Hello, ladies and gentlemen. This is a special day today. This is the second, let's say, chapter of the shooting tests of the 16th century, early 16th century Landsknecht arquebus, and I'm with Gábor Bertók. He's the director of the János Pannonius Museum in Pécs. They are in charge of the excavation of the battlefield, in the excavation of the mass graves, and they are responsible for the battlefield archaeology of the complete project. He's leading the Mohács 500 research group. I'm also a member of that group, a proud member of that group. I'm responsible for these guns, for black powder, of course, but there are many excellent scientists working in this group. Gábor, what is our goal with these kind of experiments? What do you think?
Okay, so what you can collect on the battlefield is really the debris of the battle, and the most numerous finds of those military finds are lead bullets, mostly. And in the first part of our research, we collected these bullets and mapped them also. So we have a distribution map of the bullets on the battlefield. And we also found some other weapon remains, like a fragment of a gun similar to this one, and also a part of the lock. And using these remains and museum examples, we created a reconstruction of the most typical weapon that would be able to shoot the bullets that we could find in the battlefield. And so we have a distribution map, but it would be interesting to know how this distribution happened. And for that we need to examine how these weapons worked, what capabilities these weapons had. And as far as I know, so far there has not been a systematic experimentation in this subject. And so there's one thing that we try to examine the capabilities of these weapons. And also, since most of the finds we have are bullets, these bullets are not intact. Many of them are damaged, some of them are broken into pieces, some of them are compressed. And so we have categories of these different kinds of damage, and we would also like to examine what could cause this damage in the bullets. So for that we need to experiment, and we would like to do it in a systematic way, using different kinds of targets and bullets, and reconstruction of contemporary gunpowder, for example, and also these bullets have been examined concerning their lead and other metal content. So what kind of alloys they are, and it turned out that they are alloys. Yeah. So our primary idea was that they was just simply lead bullets.
And it is quite important because the weight of the bullet and also the hardness of the bullet has a significant impact on the muzzle velocity. So, and of course in the penetration capability, because pure lead deforms easier because it is less hard, it is softer. So that will be very, very interesting to see. And it's not just about whether it penetrated the armor or not. So we have as you have just heard, we have many other questions, and probably for some of them we are going to receive the answer through these experiments. I also think so.
And also, for example, if we have different categories of damage on the bullets, and if you know what could cause this damage, it is interesting also because we have a spatial distribution of the bullets in the battlefield, and this distribution is not even. And there are areas where you have a high percentage of very much damaged bullets, for example. And so if you can tell what caused the damage on the bullets, then we can make conclusions to what event of the battle they could belong to.
Mm-hmm. Yeah, this will be interesting. We can support the primary written sources with our experiments somehow. Let's do it. The powders we selected for these tests are all associated with handguns of the age. Number 1, 3 and 7 are Italian powders. 5 and 6 are Spanish powder recipes. Powder number 6 is a unique choice, as this mix is a general handgun powder, not especially an arquebus powder. I had two reasons for trying this. First, this is the only powder where we started from a mix incorporated in a roller mill. Second, its composition is very close to today's most common formula. This will give us a good comparison to understand the effect of the roller mill on density, and also to see whether today's mix is really the best or not. The force of the powder relied on many factors, like the proportion of the ingredients, the cleanness and quality of the ingredients, the fineness of the powder of the ingredients, the time it spent in the incorporating mortars, and the size of the corns. Production was not standardized, so we can be sure that reproducing the same quality of powder was not truly possible in the early 16th century. The way we made our 5 powders was not a 100% copy of the early 16th century methods. We started the processes measuring the ingredients based on the selected recipes. The raw materials were always pure materials, fine powders, most likely better quality than what was used in the 16th century by the alchemists. This probably increased the force of our gunpowders. There was also one element that we added to the mix called dextrin, that is an organic glue. This helped the particles to stick together. This helped corning. This material is not in the original recipe, of course, but it does not contribute to the power of the powder. The 3 ingredients were carefully mixed and sheaved 5 times to ensure even distribution. According to the basic rules of pyrotechnics, 3 times through a fine sheave results a good mix, but to be sure, we did it 5 times. The greatest difference compared to the early 16th century methods was not using crushing and incorporating mortars due to safety hazards. We could use roller mills or ball mills, but they result denser powder, so we decided to stick with mixing through sheaves. So the quality we gained due to the cleaner and finer raw materials probably vanished with not using the crushing mortar to incorporate the particles. The next phase was to moisten the mix with water and alcohol. We used a 50 to 50% mix of pure alcohol and water. You must be very careful when adding the liquid, as you definitely don't want to over-moisten your mix. When it reached the desired state, corning was the next step. It is much safer and healthier to do this in moistened state, as the fine powders do not fly in the air. Corning was done as simply as possible. The moistened mix was pushed through a sheave. The granulated powder was then dried for a few days, and then the fine powder was separated again from the corns to receive a uniform powder. We followed the same procedure with each of the 5 powders.
Persze, de látod, ilyen kis szerűség. Hát, ha majd lesz benne por, azt kiszitálgatod.
We'll be using the Repro 12mm tinderl arquebus for these tests, that is based on the artifacts found at the battlefield of Mohács 1526. It is made by Kovács Armory in Hungary. The most common diameter of round balls recovered from the heart area of the battle are 10 to 12mm in caliber. This area is close to the village of Mohács. This is where the battle was decided by the firepower of the Janissary arquebusiers. The powder charges for the accuracy tests were set by a simple rule. The weight of the powder charge will equal the weight of the projectile. This is supported by 3 independent late 15th, early 16th century sources. First, this charging method of the arquebus is proven by Spanish written sources, stating that the arquebus was proved with a double charge, that meant a single ball, and double the weight of the lead round ball as a powder charge. Second, this is also proven by Giorgio Martini's work Trattato di Architettura Civile e Militare, published in 1481, stating that the small caliber schioppo, or scoppietto, the predecessor of the arquebus, was charged with a powder charge of 80 to 100% of the weight of the bullet. Third, this is also supported by a conflict archaeology find from Hungary. It is an early 16th century 11mm V-lock arquebus barrel found in the bed of the river Danube near Buda. This barrel, visible on the left, is still charged with a patched round ball. I took that barrel to CT and X-ray examination, so I could calculate the volume of the charge behind the ball. Using the average density of our Repro 16th century powders, the weight of the charge arrives here also to nearly the weight of the ball. The way I'm charging the gun is the same as what we were using when we were testing the muzzle velocity, which means that we are using equal weight of powder compared to the weight of the bullet, which is 132 grains now. The powders are the same, so they are the reproduction 16th century powders. We have 5 types of them. So altogether we are going to shoot 25 shots, and out of the 5 shots on each target I'm going to remove one, so the evaluation will be done only based on 4 shots. Okay, now comes the patch and the ball. The patch and the ball are exactly the same as in case of the muzzle velocity experiments. Just the same ridiculously high powder column in the breech. That's prime. Okay, pen closed. For some convenience, now I made this kind of a 1.5–2 centimeter long pieces, so we don't lose material when we are charging the gun. Only this small piece. A very authentic lighter, directly from the 16th century. Our first powder is sourced from Giorgio Martini's Trattato di Architettura. It is mixed from 73.7% of saltpetre, 15.8% of sulfur, and 10.5% of charcoal. The bullet is a .445 caliber lead round ball weighing 131 grains. The average muzzle velocity is 468.3 meters per secondum.
Lövés lesz.
Viszont gyors.
Megy.
This is the result with the first type of powder, which tells me that I have the first shot here, but that was definitely not caused by the inconsistency of the charge, but the inconsistency of the hold. I used a different hold with the other 4 shots, and as we are going to analyze only 4 shots, leaving out 1 for the human error, we have a group here, which is, let's say, the size of a human head at 50 meters, of course shot from a rest, which is quite far from the tactical accuracy these guns are capable of, because if you're holding it offhand, that means that the long lock time will surely affect your accuracy. It is absolutely sure. But that one is not that bad. It is not that bad. Heavy recoil, that's a fast bullet, you can feel it on your shoulder, but you're within the target without any problem. The 50-meter group of the best 4 shots out of 5 remained well in the size of a human head, meaning that the gun could cause a lethal wound at this distance. Let's not forget that this accuracy is a laboratory accuracy, meaning that you can expect less in combat when the gun is not supported on rest. Let's put these hits on an interesting contemporary image from 1514, from the letter of arms of Balázs Radák, a Hungarian warrior killing an Ottoman archer with his arquebus. This is a fair group in my opinion. On the other hand, let's not forget that in combat, the target was usually not a single enemy soldier, but a close combat formation of foot soldiers or horsemen. So we can fully accept that the gun is lethal at that distance with discharge. Our next powder is Niccolò Tartaglia's Schioppo Pio Moderna powder containing 79.4% of saltpetre, 8.8% of sulfur, and 11.8% of charcoal. Its average velocity, with a powder charge equaling the weight of the bullet, is 453.7 meters per sec. Ez gyors volt. Na, ez gyors volt. So that's the powder number 3, and the group is nearly the same as in the case of the previous one, which means that we are well within the size of the body. 1, 2, 3, 4 shots, let's say a bit more than a human's head size, and we have one flyer here, but as I told you, that's one to let go because of human errors. The group of powder number 3 was a bit larger, but the best 4 shots still remained in an area smaller than a human head, meaning that it is similarly capable powder as the first one. Our next powder, powder number 5, is a Spanish arquebus powder from 1534, mixed from 78.5% of saltpeter, 7.1% of sulfur, and 14.3% of charcoal. The average velocity of the round ball was 460 meters per sec with a full charge equaling the weight of the projectile.
Én voltam fülészetes, a jobb fülemben nekem is egy kis halláscsökkenés 2000 Hz fölött.
So this is powder number 5, the third powder in the row, and the group is, well, we have 3 shots that are quite good group, let's say half a head or 15 centimeter, but 2 flyers here. And about that one, I really thought that that was a good shot. But still within the size of the human body, and if you are shooting on an enemy close combat formation, then it's enough. Although we started with a clean bore again, the group opened up, but the best 4 shots still hit within the size of a human chest, meaning that this gun, at 50 meters, was still usable against enemy close combat formations. Powder number 6, the 4th in the row, was a Spanish general powder. This material was unique, as our mill powder mix was removed from production after the roller mill, and then corned the same way manually as we did with the other powders, meaning that it was incorporated better and had a larger density of 0.64 grams per cubic centimeter, instead of the average 0.52 for the other powders. This resulted in a stronger powder that showed in the increased muzzle velocity of 535 meters per sec. The mix of this powder is close to today's powders, 74.1% of saltpeter, 11.1% of sulfur, and 14.8% of charcoal.
Szerződjünk le, és akkor...
Powder number 6. 1, 2, 3, 4 shots, let's say in the size of a human chest, and the flyer there. And I also felt that that shot was good, which means that it's a kind of inaccuracy of the system, and in this case not me. But 4 shots in the size of the chest, which means that probably it's a bit bigger than the previous ones. But we'll measure that, and that will tell the truth. Let's check the final powder. The much higher velocity did not open up the group, and in fact the point of impact also did not change too much, showing that at this range the variation in muzzle velocity is not significant from the tactical point of view of accuracy. The size of the group is under the size of the human chest, meaning that the gun will kill. Powder number 7, or last powder, is Vanoccio Biringuccio's Schioppo powder mixed from 83.3% of saltpeter, 8.3% of sulfur and 8.3% of charcoal. This was the funniest powder. You could think that the high saltpeter content is a proof of strength, but in fact it was the weakest and also the dirtiest. It left strong yellowish residue in the bore and in the pen as well. Its average muzzle velocity was 440 meters per sec with a full charge.
Vilken sort of felicity?
Definitely not the best powder.
Even the 7th powder was not that bad. I would not say that the 4 shots here, 1, 2, 3, 4 shots, that's in a worse group than any of the other ones, which also show me that regardless of the lock time, the accuracy did not suffer. So which means that probably the shooter had a good hold. Even if it was a very dirty powder, the group did not open up significantly. It was still within the size of a human chest, meaning that the gun is still lethal. Let's summarize the results. In each case we started with a clean bore, but all in all the first powder, Giorgio Martini's Scopietto powder, delivered the tightest group. Tartaglia's Schioppo powder, titled number 3, was the second best. In both cases, the group of best 4 shots were less than the human head at 50 meters. The rest 3 powders group opened up to double size, but were still capable of hitting a man-sized target at 50 meters, meaning that from a tactical point of view, all these powders are capable of killing. And check out how dirty the gun is. It really feels that we did something today. So all the charges that we were using were enormous charges, really huge charges, and why we had the inaccuracy is proved by the patches. I collected some so you can see exactly what happened to them. So we had such a high gas pressure that most of the patches are punctured. If they are not punctured, they are clearly ruptured. And I also collected some centers. So these little pieces are the center of the patches that was cut by the bullet. So we have such a high gas pressure in the bore that these patches could not hold. Which technically means that when I was shooting these guns with a patched round ball, I was technically shooting it without patches. Interesting, again. So ladies and gentlemen, this is the Capandball YouTube channel. If you like what I do, then please subscribe, like, share, comment, because that will help us grow. Please visit us on Patreon, where you can find exclusive content from me, and also please visit us on the History of Weapons and War platform, an excellent hiding place for gun nuts like us. And until next time, stay cool and keep your powder dry.